Hello everyone. In the previous video we learned how a D flip-flop works with additional inputs, preset, clear, and a clock enable. In today's video we're going to take that theory and implement it in real HDL, then simulate it to see exactly how it behaves. So we'll go from theory to actual waveforms using Quartus and Vivado, so you can see how these features work in practice. So let's get right into it. So when you launch Quartus, this is the screen, this is how it looks. So to create a new project, you can click on New Project, Next, and then you can pick the path where you want to save it. So I'm going to save it in this path on my computer. You can pick any path that you wanted. So the project name, I'm going to call it D flip-flop. Then you can click Next. Empty project is fine. Next. We don't want to add any files. Next. You can leave this alone. Next. And then here, Questa Intel is good for me. And I'm going to pick VHDL, and then you can click Next. And here it'll give you a summary. So I'm going to click Finish. Give it a little bit of time, and it'll create the project. There you go. So to open an area where you can draw schematics, you can go to File, New, and then you can click on Block Diagram Schematic File. Click OK. And then now you can pull components and build any schematics. For this one, we're going to need a D flip-flop. You can click this icon here, Symbol Tool, and then you can search DFF. So we need D flip-flop. This one, it has a preset, it has a clear, but it doesn't have the clock enable. So DFFE, it has the clock enable input. So this is what we need. You can click OK, and then you can place it anywhere on your schematic. So as we can see, if we look at this D flip-flop, you have the bubble on the clear N and on the preset N. So that means these are active low. So 0 will enable the clear and 0 will enable the preset. Looking at the clock symbol, we don't have a bubble, so this is a rising edge D flip-flop. This is clock enable, so 1 will enable it, which means on the rising clock edge, if we give any input, we will see it on the output, on the Q state output. How many inputs? We need 5 inputs, 1 for the clear N, 1 for the preset N, D, clock, and then enable. So let's get some inputs. We can get them from here. So this is 1, 2, 3, 4, and 5. You can click escape. So let's give them some unique names. This is our D input. Next, this is the clock. So let's call it CLK. Next, the enable, ENA. Next, let's have this for the preset. Let's call it PRN. And then this one for the clear, CLRN. So in order to connect them, we saw that in one of the previous videos. So let's just branch it. Let's do that for everyone. And then let's branch also the preset, the clear, enable, clock, and D input. So let's start giving them some names. So in order to connect this D to this D input, you can connect it directly or you can give them the same name. So we'll give them the same name. You can right click properties, let's call it D. And then also this one, let's give it the same name. So this is D. So let's do the same thing for the rest. So the last one of the inputs is the clear N. So let's call it CLRN. And here we'll give the same name. So this is it for the inputs. So now we need one output to see the Q state. So you can get one output from here. We can place it anywhere, it's fine. Let's call this one Q. Then we can branch it a little bit. We can branch the output, give them the same name. So this is a Q, and this is a Q. So this is it for the schematic. So let's save the file. So you can click File, Save As. So this is our library. So let's call it D flip-flop is fine. We don't want to add this file to the project because we're going to have the VHD file. So you can uncheck this and click Save. As we notice here, we did not see the file in the project because we did not add it. So next we need a VHD file. So we can click File, Create Updates, Create HDL, and then you can choose VHDL and click OK. Then as you can see, file was successful, create VHDL file was successful, 0 errors, 0 warnings, so this is good. So we can close the report summary, and now we can open this file. You can click on Open, and then inside your library you can see the VHD file. So you can click on it, You can add file to project from here, or I can show you how you can do it if you forget to check the check mark here. So you can click open. Now this is our VHD file. So now to add it to the project, you can go to project, add current file to project, click on it, and then you see the file in here. So this is good. Now let's run the synthesis and analysis, or analysis and synthesis, to ensure that there are no errors. So you can click on this, give it a little bit of time to go to 100% in this area here, analysis and synthesis. So analysis and synthesis was successful, 0 errors, 3 warnings. You can ignore these warnings regarding the processors and so on. So this is good. Now we can close the compilation report, and this is our VHD file. Even the schematic, we don't need it, so we can close it. So next we need a Testbench file. So how to get a Testbench file? If you recall from the previous video about Quartus, you can go to Processing, Start, and then the second from bottom, Start Testbench Template Writer. Also give it a little bit of time. It was ran successfully, 0 errors, 1 warning. We don't have to worry about this warning again, so we can close the compilation report. And then now let's open our Testbench file. So if we go to our directory, so you can see a bunch of other files. So you can go to Simulation, Questa, and then if you don't see the file, you can click All Files here. And then now we see the D flip-flop VHD file. So let's open this file. And this is our test bench that we will modify to run some test cases. So first, let's save it as VHD file. So you can click File, Save As, then you can pick the type, VHD. It's okay to add this file. So let's also give it a little bit unique name at the end. It doesn't matter if it's the same name as the other VHD file, but let's call it TB, test bench, at the end to distinguish it. So click Save. This is good. So next we want to modify this file to run some test cases on the D flip-flop to see how the features behave, how the clock enable will enable the clock, disable it, how the clear, how the preset will work, and so on. So let's get started. So first, for our signals, let's initialize some initial conditions. So the clock, let's initialize it to 0. So to do this, you can add this to the code, 0. For the clear end, since it's active low, that means 0 is enabled and 1 is disabled. So let's initialize it as 1, disabled, because this is a clear and this was active low, because we saw the bubble on it. So the input, let's initialize it to 0. So let's take this, copy, paste it. For the enable, also let's initialize it to 0. So we can paste this again. The preset, also this is active low, same as the clear. So let's also initialize it as disabled. 1 is disabled or inactive and 0 is enabled. So this is good. Let's save. Also, always save as you go when writing codes. So this section here can stay the way it is. And now we want to create the clock. So how we want to create the clock, let's see how we can do this. So this is the clock period. So this will be a constant. Let's call it CLK period. Let's set it to 10 nanosecond, because this is, you know, the period is 1 over the frequency and the frequency is 1 over the period. So this will be 100 megahertz clock. So this one is fine. We can leave it alone. Let's continue our clock process in here. So this is the clock process. We'll create process for the clock. So let's call it always process. Begin. Every process has begin and end. So this is the begin end process. And this process, we named it as always. And then in between begin and end, we want to write some code. So I want to generate the 100 megahertz clock. So let's see how we can do this. Generate clock. We said 100 megahertz. So our clock signal is CLK. So let's get it. So we'll initialize it to 0. And then let's wait for some time. So wait for 5 nanoseconds. So we have the clock period is 10, so this is half of the clock period. So we can get the clock period divided by 2. This is the clock period. Copy, paste, divided by 2. And then we want to go high on the clock, so let's get this. Copy, paste, and change it to 1. And then let's wait also for another 5 nanoseconds. So let's get this, wait for clock period over 2 one more time. So this should be done. So what we did here for the clock, so let's just like recap really quick. So we initialized the clock signal to 0. And then we waited for 5 nanoseconds. And then it went to 1 high. And then we wait for another 5 nanoseconds, and then it'll go low. And then it'll repeat. So basically the clock period will be 10 nanoseconds. Because we start 5 nanosecond, we'll go high, we'll stay for 5, and then we'll go low, we'll go another 5. So we have 5 high and 5 low. So from the rising edge to the rising edge of the clock, we'll have 10 nanoseconds. So now let's write some test cases in the initialization process, code that executes only once. So first let's show normal operation. So let's wait for 15 seconds. So we'll wait for one rising edge. We'll start from the next rising edge of the clock. So we'll do wait for 15 nanosecond. Let's do a tab. And then the first test case is, let's call it 1, show normal clock operation. So which we will set enable to 1. So let's do this. So let's set the enable to 1. And then let's give some D input. Let's give it a value of 1 as well. And then we'll wait for 20 nanoseconds. We'll wait for 1 clock edge because every period is 10 nanoseconds. So we wait for 15 and then we start at the second clock edge and then we'll wait for 20 nanoseconds. So wait for 20 nanoseconds. And then what we should expect here, we should expect the Q to go to 1. Then let's also change the D to 0, from 1 to 0. Also wait for another 20 seconds, so let's take it from here. So at this instant, Q should become 0. So now let's see what happened when the clock is disabled, right? So this is the second test case, clock disabled. So to disable the clock, we need to set enable to 0. So this is enable, but we need to set it to 0 to disable the clock. And then now let's try to change the input. So D, let's set it to 1. And let's wait for 20 nanoseconds. So what we should expect here, Q should remain 0. So next, let's test the clear input. So third test case, show asynchronous clear. So first thing, we need to re-enable the clock. So this is the enable set to 1. So we need to set it 1 again, enable it. And then let's wait for 5 nanoseconds. And now let's enable the clear. Remember, this is active low, so 0 enables the clear. So this is the clear N. We can copy paste it, and then we need to enable it. So we'll set it to 0 to enable it, and then let's wait for 10 nanosecond, 1 clock period. And then what happened? Q should become 0 as soon as we change clear N to 0. So Q becomes 0. So let's release the clear. We can copy paste it and then set it to 1 to release the clear. So next, let's show also the preset input. So test case 4, show, I like copy paste, asynchronous reset. So let's wait for some times, wait for 10 because we cleared the 1. So let's wait for 10 nanosecond. And then let's activate the reset input. So let's see what we called it, PRN. So set PRN. Remember also this one is active low, so 0, that means it's active, and 1, it's inactive. Let's wait for sometimes 10 nanosecond is fine. And then at this point, Q, because this one will set the Q to 1. So Q becomes 1 immediately. And let's clear or release the reset. So to clear it, we need to set it to 1. So let's copy, paste it, and set it to 1. So this will release the clear. So this is it. Lastly, let's have a quick demo for all the pins on this D flip-flop. So 5 is quick demo of all. So first, let's set D to 0. So D will set it to 0. And then let's wait for sometimes 20 nanosecond, 2 clock cycles. So this way, Q should become 0. Q becomes 0. It'll follow D because the clock is enabled and the preset, reset, and the clear are disabled. Let's have one for the clear. So let's set the clear to 0. will enable it. Let's wait for 10 nanoseconds. So here Q becomes 0, and then let's release the clear. So let's set it to 1 again. Let's do then for 1 for the preset. So let's enable the preset, set it to 0, and then we'll wait for 10 nanoseconds. And then Q becomes 1 because the preset input will set the next state to 1. And let's also release it. We'll set it back to 1. So what else? We still have the enable pin. Okay, for the enable, so let's set the enable to 0. So that means we're disabling the clock, right? And let's give some input. So let's set D to 0 because the last Q state was 1. So if we disable the clock and we give it an input 0, Q should remain 1, right? On the rising edge should not change. The D flip-flop will keep the previous state, will hold the previous state. So let's wait for sometimes 20 nanosecond. So here, what's the expectations? Q stays 1, right? Same as the previous state. And that's it. So let's do wait. We'll stop the simulation. And this is the end of the initialization process. Here at the end, by default, we had an always a process, but we called the clock always a process. So let's just like comment it out. We can delete it or comment it out. Otherwise, it will throw an error. Okay, so this is it. So let's save and compile, see if we made any errors. So we can clear this note windows here, clear messages from Windows, and then now let's run analysis and synthesis. So hopefully we did not make any mistakes, but if we made any errors, it'll pop in here at the bottom. So let's see. Just wait a little bit until it completes 100%. So it seems we're missing a semicolon. So in line 85, obviously here we're missing semicolon. So let's add it, save, and then let's compile again. Let's clear this message window and then run analysis and synthesis again. Yes. Okay, so now we ran successfully, 0 errors, 3 warnings. So this is it. Now we can move to Vivado to run the simulation. So let's do this. We have our Testbench file. We have the VHD file. So let's go to Vivado and run this simulation and see what happens on the test cases. So create project, click next. So here you can pick your directory. I kept it in the same directory. So let's call it D flip-flop project. Click next. RTL is fine. Click next. We can add the files later. So you can click next, next, next. So we'll wait on updating until it's done. So this is good. So now how we can add files, you can right click on simulation, add sources, add or create simulation sources. So I'm gonna pick my VHD file and my Testbench file. So add files. And then this is my VHD file. So click OK. And then we need also the Testbench file. So simulation, Questa, we kept it in this path. So we added those files. So click finish. Give it a little bit of time until it's done with updating. So this is good. You can see both files, no red, that means they loaded without any issues. So let's go to settings, simulation, and then in the simulation tab, I think 600 nanoseconds will be more than enough. But if we need to run it for more than that, we can do this. So 600 nanosecond. Okay. And then now we can run the behavioral simulation. So you can click on run simulation, run behavioral simulation. Give it a little bit of time. Good, so let's go full screen on the waveforms. You can right click, full view, and let's see if everything is expected. So we can add a marker. So first, let's see our clock. So we said it's 10 nanosecond period. So this is 5, and then until the next rising edge 15, 25, 35, and so on. So our clock is generated successfully. And then here we waited for 15 nanoseconds, right, in our code to start. So let's see. Let's see our test cases. So if we go back to our code, so if we go back to our Testbench file, so the first test case is to show normal operations. So we set D to 1, we expected the Q to become 1. So let's go back to the waveforms and see. So here we set D to 1, the enable is enabled. So as we can see, Q goes to 1. So this is working as expected, right? And then when D goes to 0, we have Q go to zero again. So this is good. So let's go. What was our next test case? So 2, we disabled the clock and then we gave some D input, but Q should remain 0. So let's go back to the waveform. So this is our enable disable clock. So we disabled it at this point, 55 nanoseconds, right? And then as we can see, we gave D input an input of 1, but Q did not change because we set the enable to 0. We disabled the clock. So even at this rising edge here, Q remains 0, and which is expected. So far, everything is working as expected. So let's go back to our test bench code. Test case 3. So we want to test the clear. When we set the clear to 0, Q should go to 0 immediately. So let's see. So this is our clear, right? So at this point, Q was 1, right? Because we set the enable, we enabled the clock again. And then on this rising edge, Q went to 1. Maybe I'll zoom in a little bit. So at this point, Q is 1. And then at this point, we set clear to 0 at this point, at 80 nanoseconds. So as we can see, Q immediately goes to 0. It doesn't wait for the clock, the rising clock edge. So at this point, we disable the clear again. So let's see what was the next test case. The reset. So we enable the reset, and then Q should become 1 immediately. So let's see. This is our preset input. So at this point here, we set it to 0. This is active low, so that means, right? But Q was already 1, so it remained 1. And go back to it. So at this point, we set the preset to 0 and Q remained 1. Let's see at some other point where Q was 0. So in this area, Q was 0, and this is the preset. We set it to 0, so as we can see, it go to 1 immediately, and then it remained 1. So everything is working as expected, the clear, the preset input, the enable, disable clock, and so on. I hope this video was helpful. Thanks for watching.
Enjoyed this video? Subscribe to the Computer Engineering Notebook for more tutorials on computer architecture, embedded systems, and hardware design. And hit the bell to catch the next one.